message so that we can save some time. Okay, so I have one more small theory here in this chapter 2, electrostatics, capacitors. Okay, so then we shall move on. Capacitors. Suppose let me take two conductors of arbitrary shape. Okay, let me take two conductors of arbitrary shape. Okay, now conductors. Okay, I am going to put plus q charge on one conductor. I am going to put minus q charge on other conductor. They are arbitrarily shaped. You can't apply Gauss law to find anything. Okay, I mean to find electric field or something. So now, but what I have done here is I am going to put plus q charge on one, minus q on other. Okay, so now conductors are equipotential. Is that okay? Conductors are equipotential. So now what I do here is I am going to find the potential difference. This is at one potential, this is at other potential. I will call this as potential difference. Potential difference is equal to V plus minus V minus. Can I write like this? So potential of this one, positively charged conductor minus potential of negatively charged conductor. Now, how do you do this one actually? VB minus V. Any idea? Minus integral of VB minus VA minus integral of A to B. Am I right? Negative to positive. Let me write like this, because so I am not specifying position of whole conductor. You are going from negatively charged conductor to positively charged conductor in any path. Again, it is independent of the path. E bar dot dl bar. Am I right? Is that okay? So I can define potential difference like this, but the problem is we can't find what is that electric field. Why? Again, it is arbitrarily shaped. Gauss law will not help us to find that one. Is that okay? So, but we can define potential difference like this. Is that okay? So next idea is actually, so usually this electric field should be proportional to charge on the conductor, isn't it? So suppose if you take, so whatever you do, I mean, so whatever the formula you use, I mean, suppose electric field is equal to, what is our generalized formula? 1 by 4 pi epsilon naught integral of rho d2 by r square r cap. Am I right? Even in this case also, when you integrate it out, obviously it will be proportional to total charge. Remember, proportional to. Is that okay? So now what I do here is, again, so that total charge is the a specification of the system. Am I right? Conductors are a geometry. Conductors, so shape of the conductor, that's purely geometry. So specification of total charge on those conductor, I mean, so that is the complete specification of the problem, isn't it? I mean, the problem is specified by the charges also. Now what we can do here is, we can just take off that charge outside this one, outside this line integral. So we don't know how to do that line integral, but we can take off the charge outside. So now when we take that charge outside, look at here. So since electric field is proportional to, Q, is that okay? Electric field is proportional to total charge on the conductor. What I can write is potential proportional to total, potential difference proportional to total charge, because it is related to electric field like this. Is that okay? Argument is simple. Electric field is proportional to Q. Potential difference is related to electric field like this. So that's why potential difference should be proportional to Q. Okay, that proportionality constant we call it as capacitance. Is that okay? That proportionality constant is 1 by C, not capacitance. Is that okay? 1 by C. So this is the formalism of capacitor. Is that okay? So that's why in most of the case, whenever you need capacitance, again, look at here, once you have taken that charge outside that formalism, so what will remain actually in this line integral or something? What will remain? So the thing that remains is actually purely geometrical thing. Is that okay? Once you have taken off the charge outside that one, outside this one, so rest of thing will be purely geometrical. It depends on the what you call sizes, shapes of the conductor. Okay. So can you write couple of sentences on capacitor? Capacitance C. Okay. So this is the formalism. Now I can write C is equal to Q by V. That's how we write. Am I right? So write down. Capacitance is purely geometrical quantity. It doesn't matter whether you put a plus Q minus Q, plus 2Q minus 2Q. It doesn't matter. Okay. Capacitance, that's a geometrical quantity. So now capacitance is purely geometrical quantity. Write down. Capacitance is purely geometrical quantity. Yeah, we shall solve some problem, then you will get idea. Capacitance is purely geometrical quantity determined by the sizes, shapes, and separation of two conductors. Yeah, the question. And separation of two conductors. Yeah, I hope you know its SI unit is farad, isn't it? So how do you define 1 farad? Again, coulomb per volt, like that. Is that okay? Again, you can go for that formula. Now you should now in many cases, suppose if you need a capacitance, you have to go to this formula. Okay, you have to equate these two. So in that equation, again you have to take off that charge outside. Whatever remaining, you can put it as a capacitance. Is that okay? You can just have this kind of equality, take charge outside. Now remember, they will give only conductors. You can assume there is a charge, plus Q on one, minus Q on other. Then you can proceed. As long as there is a charge, again there will be electric field. You can line integrate this one. Is that okay? We shall do some problem on this one. So again, example number 2.11. Parallel plate capacitor. Yeah, so for capacitor, so V is equal to V plus minus V minus is equal to minus integral of negative to positive E bar dot dl bar. Okay, so V is equal to 1 by C into Q. Now let me take parallel plate capacitor. So parallel plates, okay, you have to find the capacitance. Is that okay? Shall I take like this? So parallel conducting plates. So they are separated by a distance d. Okay, they are separated by a distance d. Cross sectional area A. I hope you solved one earlier problem. What is the electric field in between the capacitor? Isn't it? He extended that infinite plane problem to that one. Is that okay? So just solve that one. I think yeah. So in this chapter only, isn't it? Soon after infinite plane problem, he discussed what is the electric field in between the plates of the capacitor. A kind of capacitance arrangement. So now he will give only this one. This is the geometrical arrangement. Am I right? Two conductors. It's a kind of I just defined the geometry here, isn't it? Now, if you want to find the capacitance, then you have to go for that formula, isn't it? So if you want to go for that formula, then you have to put some plus Q on one, minus Q on other. Is that okay? Let me put plus Q here, minus Q here. Is that okay? Let me put plus Q on one, minus Q on other. Is that okay? If I put plus Q, what is the surface charge density? Obviously, it will be uniform, isn't it? Very thin sheet, okay? So, Q by A. What is the surface charge density? Minus Q by A, isn't it? Because I think you remembered electric field in terms of surface charge density, am I right? Electric field between the capacitor is sigma by epsilon naught, am I right? Due to one infinite plane, sigma by 2 epsilon naught. So, due to two of them, it will add up and you will get sigma by epsilon naught into some, from positive plate to negative plate, isn't it? Now, again, I am going to take the same idea here, okay? So, my electric fields are like this. For some from positive plate to negative plate. Now what is my electric field value? Sigma by 2 epsilon naught into, let me choose this is as some n cap, okay, some n cap. Now what is sigma? Q by A by 2 epsilon naught into n cap, that is my electric field from positive plate to negative plate, isn't it? It's very simple. Now what I have to do here is, I have to do line integral from negative to positive, negative plate to positive plate, line integral of electric field E bar dot dl bar. Where? Okay, by epsilon naught. Why I have written 2 epsilon naught? Just I said epsilon naught, isn't it? Yeah. Wait a second. Electric field is equal to sigma by epsilon naught into n cap. Is that okay? Sigma is charge by total area, epsilon naught into n cap. Is that okay? So now look at here. Now I know electric field. Now I am going from negative plate to positive plate. But observe one thing. When you go from negative plate to positive plate, isn't it? If suppose if you take dl as positive, but I mean electric field and dl vector both are in the opposite direction, isn't it? So now but in polar coordinate different thing will happen. I think I have discussed that one. Okay, this question will come here again. Whatever we have done, I mean while integrating from infinity to r, do you remember? We haven't put one more negative sign. But here we are putting one more negative sign. Why? Here my dl is positive, or change in length, or L2 minus L1, that is positive. So that's why it will not introduce any sign, remember. So that's why you have to take care about this dot product. So that's why. So mod E mod dl into cos of 180, where dl will be positive in this case. Cartesian dl will be positive, I mean always positive, remember. Is that okay? So now again I'm going from negative plate to positive plate. Is that okay? Any path, and let me go in a straight line, isn't it? That's best idea, because if you go by a curved path, I mean this will be lengthy, am I right? This integral will be lengthy, and this integral is always independent of the path. So that's why let me choose straight line from negative plate to positive plate, and I'm moving opposite to the what you call electric field direction. So that's why negative sign will get cancelled. Electric field is constant, am I right, throughout your path. Integral of dl. What is integral of dl? Negative to positive, straight line. D, distance between the plate, isn't it? So electric field into distance between the plate, am I right? So V is equal to, now look at here, do you remember we had this formula? Or electric field is equal to V by D, isn't it? We had this formula. Again, our aim is to define what you call capacitance. What is electric field now? Q by A epsilon naught, okay, into D, am I right? Now what should I write? V equal to 1 by C into Q. Don't write V equal to C into Q. Okay, I mean I'm taking this one because V is, again look at here, proportional to Q. The rest of all factors were geometrical. You can see that one. Distance between the plate, area of the capacitor, isn't it? Those are geometrical factors. Look at here. So that's why C is equal to epsilon naught A by, isn't it? Why I have taken? Because I can just write again potential proportional to charge and rest of all factors, geometrical factor, that is 1 by C. Okay, that is defined as 1 by C. So do it yourself again. Line integrate, you have to line integrate from negative plate to positive plate, then that's called as potential difference. V plus minus V minus negative plate to positive plate, E bar dot dl bar. Remember, in this case, you have to take care about the dot product because dl is positive. You are moving with increasing L. Is that okay? Yeah, speak out. Or if you have chosen origin somewhere here, okay, suppose again there will be always confusion here in this line article, okay. Let me choose origin here. Let me take this is as x cap. Is that okay? Now when you go from negative plate to positive plate, obviously your dx is negative, isn't it? When you go from negative plate to positive plate, your dx, this is the origin, okay. Let me take this is the origin, this is positive x-axis. When you go from negative plate to positive plate, obviously your dx is negative. Can you feel that one? When you move along positive x-axis, dx is positive. When you move along negative x-axis, dx is negative. Am I right? Now look at here. I am going to write dx, dl vector in this case, dl vector that's equal to dx into x cap. dl vector equal to dx into x cap. Let me just proceed. What would happen? We shall see. Okay. So now electric field is also along x cap. Is that okay? Let me write mod E into x cap. When I take this dot product minus mod E, integral of dx will happen from where to where? From d to 0. You got one more negative sign. I get to my point. I think this is the best way. There is no question, isn't it? There is no question. From where to where you are integrating d to 0. Do the integration, substitute the limit, you will get negative distance, isn't it? It will introduce that one. Is that okay? Our coordinate geometry will take care actually. If you purely go via coordinate geometry, you don't have to worry. It will take care. Okay? But if you are integrating as it is, you have to take one more negative sign. Otherwise, you will end up with negative sign. Okay? So obviously, positively charged conductor should be higher potential than negatively charged conductor. And this should be positive. That potential difference, that should be positive. Yeah, any question? Yeah, so try to do in this way. Okay, by choosing the origin of the coordinate on the positive plate and towards negative plate x-axis. So do it like this. Okay. Let me take one more. This is example number 2.11 or 11th example. Okay, example. Let me take one more example. Yeah, use this idea. Okay, use this idea. Last idea. 2.12. Find the capacitance of two concentric spherical metal shells of radii A and B. Yeah, today I am a little bit confident. Told if you can draw circle properly, you are confident. Yeah, just forget about it. Okay. What they have given is they will give only, yeah, speak out quickly. Yeah, it's an infinite plane assumption. That's correct. That is due to one of them. So just see, just refer again. Let me example number 2.6. Okay, example number 2.6. He discussed that one. He used that again that superposition principle. He assumed there exists only positively plate only positive plate, and find the electric field. There exists only negative field. Find the electric field. So in this region, above and below, those effects will get cancelled. In between, those effects will get added. Field will get added. So that he has added that one. Is that okay? Sigma by 2 epsilon naught, sigma by 2 epsilon naught. So this is the electric field between the capacitor always. Okay, that's the assumption again. At the edge, it will not be straight line. Obviously, at the edge, it will go like this. Okay, so I haven't taken care of that one. The assumption is area is too large compared to the what you call distance between the plates. So that's why we can have that assumption. I mean, now whatever the region between the capacitor, so that's very close to any of those plane. So that's why that infinite plane assumption is true. Okay. At the edge, actually, this will happen. Like this, it will happen. Okay. At the edges. Yeah. Yeah, wait a second. Don't go for that one. So that will be ambiguous. So do it in pure coordinate geometry. So take this one as origin, positive plate. So take, I mean, your x-axis along negative plate, from positive plate to negative plate. Is that okay? Perpendicular to both of the planes. Is that okay? So now, obviously, your electric field is along x cap. So then choose your dl vector dx into x cap. Isn't it? Or even if you choose other part of dl vector dy into y cap like that, I mean, your dot product, it will get cancelled, isn't it? So now, dl into x cap, because you are moving along straight line, take that idea. Is that okay? So now, look at here, when you integrate this one, isn't it? That negative sign will be remained. When you integrate, you have to integrate, you are going from, your line integral is from negative plate to positive plate. You are going from x equal to d, x equal to d to x equal to 0. It will introduce one more negative sign. This is minus d, isn't it? Minus mod of electric field into minus d. Okay, it will take care. Ultimately, it is positive. Negative plate to positive plate, you have to run your x integral from d to 0. Yeah. Here dx is minus. Correct. That negative, all those negative added to give negative. Okay. So it will get cancelled. Suppose if you are thinking that your dl is positive, use cos 180 degree, and that will place one more negative sign. This is pure coordinate geometry. You better choose this one. Is that okay? Yeah. So now next problem, in this one, you have purely geometrical situation. Definitely he will give only geometrical situation. Yeah, any question? Yeah, dx is negative. That's why, no, that integral, that technique will take care, isn't it? You are negative, dx is negative, you have added, you got total negative. When you go along negative x-axis, your dx is negative, am I right? Those negatives are added to give minus d, isn't it? So integral as a summation, if you think like that, isn't it? You are integrating from here to here, you are adding dx here. Those are, yeah, definitely that gave negative quantity. D is the lower limit. So minus into minus will be plus. No, look at here, d upper limit minus lower limit. X upper limit minus lower limit. You got negative. Upper limit minus lower limit. So that quantity, integration quantity is again negative. Huh. D will be in the lower limit. So minus into minus. No, I mean, yeah, look at here. Yeah, that negative sign that I have taken. So this is x running from d to 0, upper limit minus lower limit, 0 minus d. Yeah, you got your last answer negative. Look at these two. Isn't it? That integration technique is like that, am I right? Summation. Summation of dx1, dx2. Just forget about those limits. Integration dx will be a negative quantity. Yeah, I mean from where to where again. So if you are moving along positive x-axis, definitely you will get positive, isn't it? Suppose if you have moved from 0 to d, you will get positive. Since you moved from d to 0, you get negative. Okay, so this will play the role here. Okay, not only here in your that. So look at this problem. In that one, same question comes. Okay, better to handle that one in pure coordinate geometry, because it will take care. Our integral techniques will take care actually. Okay, limits everything. Now, the next problem is again this one. So in this one, again he will give only geometrical situation, but you are free to assume charges. plus Q on this one, minus Q on this one. Is that okay? You are free to assume charges. Ultimately, capacitance is independent of the charges on that one, okay? So we are going to take that charge outside and we are taking that proportionality factor, okay? Yeah, any question? So now look at here. So what is the electric field? I hope you know, you solved this problem. You can apply Gauss law, am I right? Spherical symmetry. These are shells, okay, metal shells. So charges reside only on the surface, okay? There will be no electric field outside or inside the inner one. Okay, electric field exists only in between. Can I write electric field? Again, if you apply Gauss law, 1 by 4 phi epsilon naught. So Q by R square into R cap again, isn't it? Because if you take any Gaussian surface which is concentric with the center, okay, because that Gaussian surface will enclose this Q charge and Gauss law will give this one, isn't it? You should have applied, you should have practiced Gauss law in such a way that you have to quickly apply Gauss law and you have to write this one. Is that okay? Now, so next one is, again, this is positive plate, this is negative plate. Okay, this is positive plate, this is negative plate. Now you have to integrate V is equal to V plus minus V minus. If we were to do in pure coordinate geometry way, here we learned that one, remember, okay? So otherwise ambiguity will come. Minus negative plate to positive plate, E bar dot dl bar. Okay, right, take dl in polar coordinate. Okay, take dl in polar coordinate and do that one. dr r cap plus and so on, isn't it? When I take this one, V is equal to minus Q by 4 phi epsilon naught, am I right? Q by 4 phi epsilon naught, 1 by R square from negative plate to positive plate. When you are at negative plate, what is your radius? B. B is the negative plate, am I right? Positive plate, Q by 4 phi epsilon naught minus 1 by R, minus I have taken outside, B to A, Q by 4 phi epsilon naught, 1 by A minus 1 by B. B is higher, that's positive. Am I right? B is higher than A, is positive quantity. Yeah, you better not to think of that cos 180 degree. Is that okay? Our integral will take care. Now what is, apart from this Q, what is this whole quantity? 1 by C. Don't write it as C, okay? That's 1 by C. That's why your capacitance is equal to 4 phi epsilon naught 1 by A minus 1 by B, or take LCM and write that one. 4 phi epsilon naught AB by B minus A. That's it. Isn't it? Purely geometrical one. Wait a second, let me extend this one. Suppose if you have only one conductor, one spherical sphere, sphere will be always spherical, isn't it? Now sometimes while drawing it will not be spherical. That's why I told like that. Wait a second. Yeah. Now I'll put B to infinity. I'll make B to infinity. Now look at here. Whatever the electric field you got here, if there were no this plate, this shell, you would have got same electric field in this region, but outside also electric field extends, isn't it? Now where electric field ends? Electric field will end at infinity. Now where are negative charges? Negative charges are at infinity, isn't it? Where our electric field will end, isn't it? Now if you have only one sphere, one conductor, one spherical conductor, that also a kind of capacitance configuration, isn't it? Where is other conductor? It is at infinity. So when you put B to infinity, now what is that? Your capacitance 4 pi epsilon naught divided by 1 by A, isn't it? The only one conductor or only one conductor will also constitutes a capacitance arrangement. Where is other conductor? Suppose if you put plus Q charge on that one, where is minus Q charge? It is at infinity, isn't it? So I can just generalize the same thing. So this is for sphere. This is the capacitance of sphere 4 pi epsilon naught into A. Am I right? Can I say like that? Capacitance of only one sphere. Is that okay? But to use this one, you should assume other sphere at infinity, like that. Okay, I just extended this argument. So just have a note on that one. Yeah. Then also, I think you have to integrate from your electric field will be minus r cap. You have to integrate ulta. It will take care. Okay, you can choose in any way. That's correct. Okay, you can take plus q outside, minus q inside. Then also you'll get the same answer because electric field will be ulta. Okay, electric field will be ulta, and your integration will be ulta. We have done B to A, then you have to do A to B like that, isn't it? Negative plate to positive plate. It will take care. Okay, you can assume charges in any plus q in any plate, minus q in any other part. Okay, plus q in any conductor, minus q in any other conductor. Suppose I am charging a capacitor. So now equation 3.8 is referring equation 3.8. Wait a second. Do you remember our VB minus VA? It was work done in moving the charge from A to B. Am I right? By charge. Now what I do here is I am going to move small dq charge from positive plate to negative plate. That's how we do charging. Am I right? Using a battery. We are taking off charge from one of the conductor and we will push that one to other conductor. That is the process of charging. Are you getting my point? You are charging process means taking the charge from one of the conductor of the capacitor to pushing that one to other. Is that okay? So now look at here. I am going to take a dq charge from one of the conductor and I am going to put it into other one. Is that okay? Then what would happen here is, so potential difference, how I can write potential difference? Q by C. Suppose Q is the instantaneous charge. Q by C, potential difference is equal to W by dq. And that work done is very small work done. Isn't it? Work done in moving small dq charge. Suppose instantaneously one conductor is at plus q charge, other conductor is at minus q charge. Okay. Now what I do here is I am going to take dq charge from this one. No, dq charge from this one. I have to plus dq charge from this one. I am going to add this one to here. At that situation, what is the potential? What is the potential difference? This is the potential difference. You are moving the charge from minus to plus. Am I right? Again, that's why potential difference is V plus minus V minus is line integral or whatever you do from that one, ulta. Okay. So that's why potential, or I better write like this. Okay. Or let me write W is equal to Q into VB minus VA. W is equal to Q into VB minus VA. Okay. Now, small amount of work done is equal to small amount of charge transfer from positive plate to negative plate. V plus minus V minus. Can I write like this? V plus minus V minus. So potential difference. That is the potential difference. Is that okay? Now what would happen here is, what is V plus minus V minus V? So potential difference. So dq. V I can write as Q by C. Q is the instantaneous charge on the capacitor. Okay. dq dw. Now when you integrate this one, what would you get? Total work done. So in what you call transferring all q charges. Is that okay? You can integrate from 0 to q naught. Let me say q naught is the final charge after transferring all of them. So q by c into dq, what is that one? Q naught square by 2c. Or write it as capital Q naught, because small q you have taken, capital Q naught. Q naught because that's a constant, I mean final charge on the capacitor after complete charging or something. Okay. Now this little difficult to remember this formula, that is the total energy stored in the capacitor actually. What is that? Square. Q square by 2 running from 0 to Q naught. Okay. To that integral. Q naught square by 2c. So that's why what we do here is I am multiplying and dividing by c. Q naught by c the whole square into c. Can I write like this? What is Q naught by c? That's a maximum potential difference. Am I right? I can write as half c V naught square. It's a kind of half mv square formula. Is that okay? Don't say v as velocity. Here it is potential. A kind of this formula. Similar formula will come in the inductor also later. Half I, not half I omega square is your rotational dynamics. Half Li square. Am I right? Like that it will come. Do 2.43, 43rd problem. Okay, and we shall close this chapter now. 2.43, 43rd problem, and 2.49, 49th problem. 2.50 I told already, very important. 2.52, let me solve some of them in the in between. Okay, and shall close this chapter for a time sake. Yeah. Question. So what's the time? Planar symmetry, spherical symmetry. That problem is cylindrical symmetry. Just do that one. Use Gauss law to find electric field. Suppose if you don't remember electric field, here you can directly write electric field. Okay. If you don't know electric field, use Gauss law quickly to find the electric field for cylinder. Okay. Example number 2.43. I am talking about that one. Okay.